Oh yeah, so okay, I'd like to see this.
You wanna...
This is good.
All right. I'm gonna mute you guys for a second here, okay?
Yeah.
All right, there you go. Well, good morning, everyone, and welcome to the last seminar of this semester. It is our great pleasure to have here with us Professor Sigrid Adriaenssens, who comes from Princeton University. She's a professor in the Civil and Environmental Engineering Department, and she's the director of the Form Finding Lab. So in her research, she basically studies the mechanics of large span cells and membranes. And she does anything really, from analytical formulations to numerical form finding methods, develops algorithms to try to understand these interesting systems. I'm not gonna go over the whole list of awards that she has, because I could just take very precious minutes from your presentation. So I'm gonna just name a few. So just 2021, she was named Fellow of the Structural Engineering Institute of the American Society of Civil Engineers. She was elected Vice President of the International Association of Cell and Spatial Structures. She received the Digital Futures Matthias Ribman Award and the Pioneers Award for the Spatial Structures Research Center at the University of Surrey, UK. So that's just to give you a taste. That was just 2021. So Sigrid, thank you for being here, and the floor is yours.
Okay, can you hear me well? Yeah.
Yes.
Well, thank you very much for having me. It's always a pleasure to be in Miami and to come to Miami. I'm gonna delve right in. Wait, hold on, let me see. Yes, so I'm originally from Belgium, and about 12 years ago now, I moved with my family from Belgium to the United States. So I'm based in Princeton. And during the weekends, we like to go to the New Jersey shore. This is a picture taken from the car when we're driving to the New Jersey shore. And what I kind of every time notice is these huge bridges. They're very massive. And it always surprised me because, you know, the construction industry is one of the most resource intensive sectors. So it seems to me it would be a good idea to reduce the amount of materials that we are using. And actually, you know, if you make like an integral bridge, this is actually more the shape that would be more efficient. So if you can use less material, that is more cost effective for the client, but it's also better for the environment because we have a smaller carbon footprint. And then when we get to the shore, this is what we see. This is actually a Rockaway Peninsula. This is in near New York. And we see a lot of people enjoying the water, but also a lot of people on the beach and a lot of buildings right next to the beach. And we know that the world population is going to increase by 50%. It's going to increase by 2.1 billion by 2050. That means that we're going to need a lot more floor area. And when we look at that and we look at the productivity of the construction industry, that we see that the industry has really kind of gone down, especially in the United States, compared to all the other industry, and yet the construction practices haven't really changed. We see that we use a lot of materials, and some of these materials are not going to be so readily available anymore. This is, for example, sand. It's not going to be really available anymore. And the construction industry produces a lot of construction waste. About 29% of construction waste ends up in landfills in the US. We produce a lot of CO2 emission. This is mostly by making of concrete, actually more specifically by the making of cement. And we also suffer the consequences of climate change because we are getting higher loads that we have to incorporate when we're designing buildings. So usually what happens is, so we had a big storm. The previous picture that you saw was Hurricane Sandy, which caused a lot of damage to property in New Jersey. And what happened after Hurricane Sandy is that people went back to rebuilding their communities in the way that had been before. So they just basically rebuilt the boardwalks. Or other options, this is in brick. This is New Jersey, one way of dealing with climate change is just to build huge walls. And that, of course, prevents people from going on the beach, but it also prevents animals from migrating from the sea onto the land. And of course, it diminishes property value. So this is, I think, really not a good idea. So we need to change what we design for, how we design, and how we build. And so my proposition is to build slender surfaces. So as Professor Pestano mentioned, my research is on shells, membranes, nets. And we're going to use, instead of mass, we're going to use geometry. So we're going to make geometry work for us. And if we do that, we can actually leverage mechanics in geometry that does very interesting things. And we also have to think about how we are going to construct differently. And I propose that we look at self-assembly processes. Now, I'm not the first one to use form to build. So this is a plot. On the x-axis, you see time. On the y-axis, you see weight, kilonewtons per meter squared. And at the top, you see the pyramids. Of course, they're very massive and very big. This is a logarithmic scale, by the way, the weight. And then as we make our way down, we have the domes. For example, we have the cupola of the Hagia Sophia. We have the Gothic cathedrals. And then when we get to the 21st century, and this is what you see now is kind of a close-up of the 21st century, we have a project that I worked in. So and you also see that I've drawn a line here. That line is the loading of the wind. So wind, is in the order of 1 kilonewton per meter squared. Some of these structures that use form are actually lighter than the wind. So that means that if they are not properly designed and a strong wind comes along, they will just fly away or get damaged. I'm going to show this project because this was a project I worked on before I joined academia. This was when I was working for Laurent Ney in Brussels. We got invited to participate in this design competition. This is the Dutch Marine Museum, which originally was a gunpowder warehouse. So basically the Dutch in the 16th and 17th century would stop at this building, stock up on gunpowder, and then sail out into the world to do whatever they had to do. At that time, they were very good at making boats and very good at making maps and developing maps. And after this was a gunpowder house, it became a prison, and then it became a museum. So when they were renovating the museum, the architect said it would be really great if because this is now a plan view, so looking from above of the museum, it's actually not one building, it's 4 buildings with an open courtyard. It would be great if we could cover that courtyard because this is in Amsterdam, so it means it rains a lot, it snows a lot. If we could actually use that space for ticketing or events. So it was an invited competition, and in the museum we found this map here. This is a map of the world, what the Dutch thought the world looked like in the 16th or 17th century. And you see they get some parts wrong, but the other thing that you see is that there are wind roses on there, so there are points there. And these points are connected together, and that creates an interesting geometric grid. So we wonder whether we could use that grid. If you imagine now this being the courtyard's about 90 feet by 90 feet, so 30 meters by 30 meters. If we can extract this geometry, here it is imposed on the courtyard, but we also know that we can actually not make this structure as a flat structure, right? We cannot make this as a beam structure because then the beams would be enormous. So we have to develop it into a cupola or into a compression-only structure. So this is now 2000, the time was 2006, 2004. So we modeled this as a hanging chain model with some restrictions, and actually started from the flat geometry and then let this be hanging chain model that produces, when this is inverted, a compression-only structure. And we ended up with a dome. So here, fast forward a couple of years, this project was chosen to be built. Here it is from a bird's eye view. This is what it looks like underneath. What you've noticed is, first of all, I hope that you recognize the map, but also you will see that these members are actually very, very thin. And that is because the shape of this is a form-found shape. So that means that it's mostly, all these members are mostly under self-weight actually loaded. And so they can be very thin. The other thing that we did is that at the nodes between all these points, we put LEDs. So this is at night. And you see here the reference to the maps and the sky that the Dutch might have seen when they were sailing. So when we build this, afterwards I got to think, well, this is actually a really good structure. This is an indeterminate structure. That means that, if there is damage, if one of these members gets damaged, this structure doesn't fall down because there are many load paths through this. So the forces can find their way around the damaged area and then go to their supports. It is, there's not a lot of material in here. This is steel, the rest is glass. The glass doesn't really act structurally, so it's just really the steel. And that is, of course, because it's a form-fired chip, because it's this hanging chain ball. And secondly, the other thing is actually really stiff. And that is also because of the form. If you think about seashells, also they're very thin, they don't use a lot of material, but because of their shape, they're very curved, they're very stiff. And so I put this slide up because I think often, when we compare ourselves with other engineering disciplines, we kind of sometimes miss out the very obvious, the huge challenges that civil or structures face are, first of all, we work at a very large spatial scale, right? So the things we do are at the scale, I put here 10 to 100 meters, but I could have put 0.1 meter to 1,000 meters. So the scales are very big. And as we know from Galileo, we cannot scale up things, so something that works, a little bone that works at that scale when scaled up. If you scale up the area and you scale up the volume, it doesn't scale up to the same amount. So that bone would look like that when it's scaled up if you have, for example, bending, right? So we cannot just scale up small things to big things. The other big challenge is time. In other engineering disciplines, when we design something, for example, we design an iPhone, it will last, I don't know, a year, 2 years, might last 10 years, but not 50 years, not 100 years, not 500 years, not 2,000 years. And that's the scale that we are working in. So basically, whatever we're designing has to stand up to all the events that are going to happen during that time. And I've got here the dome in Florence, the Santa Maria del Fiore, which I'm going to come back to, which has obviously this beautiful dome, but has stood up through earthquakes, right? And that brings me to our third challenge is, of course, the things we design are very big, they have to last for a very long time. And so the materials that we use are also limited in that way, right? We need to use materials that are going to last that long, and that can be used at these kind of scales. And that is unlike in nature where you have many different materials. And then some other challenges. I'm going to talk about other challenges in a second. But so I'm going to talk about resilient and sustainable slender structural surfaces. I already mentioned I'm looking at shells, nets, membranes. And all of these use very little materials, so they're very cost effective, and they have very low carbon footprints. And I've chosen to choose these three projects. So I'm going to look at flexible shells, at nets, and at rigid shells. And these kind of surface structures, what's really amazing about this is that they can have properties that other conventional structural systems do not have. For example, being column systems will not be able to amplify motion or move. Or you will not have things that can change their stiffness or that can carry very heavy loading. And all these slender surface structures can do that. I'm going to show you a little bit about that. So I'm going to talk first about the flexible shells. It's a project that London still worked on. So anyway, so imagine this is a rendering. So this is not a real project. This is an imaginary project of a museum in Texas, Marfa. Sometimes in buildings, if we want to conserve energy, whether it's for lighting or heating, we might want to have filters on our facade that actually control the amount of solar radiation and the amount of lighting that comes into the room. And so, or for example, you might have in a building different programs, right? So for example, here you see some openings, areas that are very open. Those could be maybe conference rooms where you want lighting, but then maybe the more closed areas are areas where you have exhibits. So you want to reduce the amount of lighting. Or maybe at the nighttime, or this is twilight time, you want to get a lot of lighting come in. So sometimes you want it to be like this, or maybe this is at noon, you want your facade to be pretty close, a little bit like the facade here. And it has been shown, this is not my study, but it has been shown that if you have adaptive facades, you can save about 40% of operational energy costs. So we worked with a botanist on looking at mechanisms that we can find in nature that actually open and close. Now you might think plants don't move, cacti don't really seem to move, but sunflowers move. And so with this botanist, we identified 5 strategies of how plants move. And so we are interested in large movements for adaptive facades and limited actuation. So we want to put in very little energy and have a very large movement. So one is what we call differential expansion. So that is if you have cells and one series of cells swells with respect to the other cells, you will get, in this case, bending. That's differential expansion. You can have very thin elements, like this is the flower of paradise. Very thin elements. If a bird goes and sits on this will twist, right? So torsional buckling. Another way that nature does this is by layered material anisotropies. So basically, if you have materials with different fiber orientations, and if they swell, they will either warp or bend. Then the one that we all know, the Venus flytrap, which is basically shell mechanics, where you have shells that when there is a trigger will deform a lot. In this case, this is snap-through buckling. So this is a very fast, uncontrolled movement, which we don't really want for a facade. We don't want it to open, close, open, close. And then there is a release of elastic energy. And so we are actually most interested in the shell geometry mechanics. So basically, in nature, it's more efficient to bend than to stretch, right? So if something has to deform, it will rather do it through bending. But as I said, we were not so interested in employing the Venus flytrap because that is too explosive. It's not through buckling, but we were interested. We found this flower here on the left, which is the Celidium gramineifolium, which is a flower that grows in Australia, which actually moves to pollinate. So there is you see here, there's maybe I'll show it here. There is the pink part, that is the active part. The blue part doesn't really move, that doesn't really change shape, but it just has like an active part that can change its shape and cause a large movement in there. So actually that shape is an antiplastic surface. Actually, if you take a Coke bottle, it's the middle part of the Coke bottle. If you squeeze that part just a little bit, if you just put a little bit energy in it, it will actually open in a big time. And so we were interested in that geometry. Actually, we found that Lord Raleigh had said something similar, because one thing is to extract these geometries from nature, but the other one is to actually find an engineering method to discover them. And so Lord Raleigh had said that when the shell is thin enough and is vibrating in one of the grave possible modes, the middle surface behaves as if it were inextensible, right? So these are isometries. So basically, if you want your form to deform in a specific way, one way to do that is just to look at the Eigen Frequencies. And that are the modes that these surfaces want to deform in very easily, right? So for the application that we were looking at, adaptive facades, we found that this antiplastic curvature that you see here, the yellow one here, works really well and can both bending and twisting in a surface. So we did lots of parametric studies to see whether we could actually develop this into an adaptive shading device. And here are some renderings of what that device, when it's fitted on an office, would look like. So this is the twisted motion. This is the bent motion. So it's important also with adaptive shading device that you not only control the lighting and the heating, but also that you control the view. This is when it's half open, and this is when it's closed at night. I'm now going to talk a little bit about nets. And this project started because I got a phone call from Professor Adi from the island of Réunion, which is in the Indian Ocean. And he knew that I was like modeling shells and membranes and nets. And they had a big problem in the island of Réunion. So it's a beautiful island. It's next to Madagascar. It's part of France. People go there for nature, but also a lot of surfers go there. And they had a lot of shark attacks recently. So the government had decided to put on 2 beaches a shark barrier. Basically, these are nets to keep the sharks out. On the right-hand side, you actually see a schematic illustration of this. This is what they installed. So as you can see, the materials are not very high quality engineering materials. There's anchor chains, so that is attached to the floor. Then there are buoys. Then there's a polypropylene net with a 40-centimeter mesh. That's to let the turtles go through. And then there's buoys at the top. Now, what happened? These nets were very expensive to install, not because the materials are expensive, but because it has to be installed by scuba divers. And every day, scuba divers have to but through all the nets to see if there's any damage. So very expensive, millions. After 2 months, the nets were already broken. And that's when Professor Adi called me. I thought, well, it's probably the sharks that are nibbling on the nets, but that was not the thing. And very hard. I will turn down the volume a little bit. You see here on the right-hand side, this is a movie of when they're inspecting the nets. On a normal, calm day, the sound is the sound of the scuba diver. Maybe I'll switch up the sound. And so what we are seeing, these nets are installed in the wave break zone, right? So this is the zone where, first of all, you get dynamic loading. Secondly, the water levels go up and down and up and down a lot. And this is then just during a normal day. It's not even during the cyclone, like the water levels rise. So we model these nets and have them interact with waves. And so what we see is, the kind of animation in the middle is the current design, right? So they have like an orthogonal net. And what you see when a wave comes along, because the cables are oriented vertically, they cannot really, when the boys want to extend more, they cannot actually extend more, and they get highly stressed, right? In contrast, for example, if you put a hexagonal net next to it, and actually these are the kind of net that they use for example, soccer goals, you can see that that net can extend a lot more, and the stresses in it are much smaller. So basically, we studied like 6 different kinds of net topologies, and we looked at different wave orientations. What if the wave is coming along? These would be rip currents are coming perpendicular to it. And that's what you see on the left-hand side. You see they all kind of behave the same, except for there's one really bad one, which are 6 elements, orthogonal, has high tension. That's of course the one they constructed, right? So they constructed from all the nets the worst one. And of course, actually the tensions are not that high, but it's of course commutative tension, right? So it's like fatigue going on, off, on, off, on, off. And then if you imagine that there are grains of sand, also going into the nets, we kind of postulated that that is what caused damage. What's kind of interested in these nets is that because the tension changes, the stiffness of these nets also change, and I think that is an interesting property that these nets have. That they get geometric stiffness. So as you increase the loading in them, which in this case is not really desirable, but for other applications this might be very desirable. As you load them more, they become stiffer and stiffer. And because I had been working on this project, I got contacted by Rebecca Lazier, who's a choreographer in Princeton. She works with Janet Eckelman, who is a visual artist, world-renowned visual artist, who makes big net sculptures. And they were collaborating on a project of nets where they see the nets also as a dancer. So not so much as a prop in the background, but actually the dancers are dancing with the net, or the net is dancing with the dancers. And so they're very much interested both in what choreography can we get out of that, also visually, how can we have the net have very dynamic expressions. And so we work together actually in an architectural studio at University of Washington with Tiger Sprague. And we are now carrying this project forward. So we actually have a research project together. I'm studying how we can, through loading, change the stiffness of the nets, and that's of course a function of where they are suspended, but also on how the topology is arranged. So you see here these 2 animations. On the left hand, you see the orthogonal one. That's the one from the shark nets. But if you put them on the bias, so basically you now change the orientation at 45 degrees. It becomes a lot more flexible, which was very good for the shark nets. It can extend a lot more, has a much what you would say like a better Poisson's ratio. Okay. Oh, I was going to show a video, but I'm going to move on also in sake of time. I'm going to talk about shells. So I've talked about flexible shells for the adaptive facades. I've talked about nets. Now I'm going to talk about rigid shells. And so for those amongst you who know anything about shells, and actually you have a beautiful shell here, you have the Miami Marine Stadium that has like withstood many hurricanes. We know that shells resist very, very high forces, whether it's from earthquakes or hurricanes. And we set out with my students to find out why that is. So we studied this particular shell here. So a shell is a very slender surface that is curved and is rigid. And this particular shell here is designed and built by Felix Candela in Mexico City, a very much earthquake-prone zone. And the shell in these earthquakes has not really experienced much damage. So we carried out analysis to see why that is. Well, first of all, we found out that during an earthquake, all the stresses are within acceptable limits. But what is more interesting actually is that the frequency of the earthquake, which is very low, is 0.5 hertz, is far away from the Eigen frequency of the shell. So that means that the shell is actually really, really, really stiff compared to, for example, to beam column systems. The Eigen frequencies would be much lower. And when your Eigen frequency is very close to the frequency of the earthquake or of the frequency or the waves or whatever frequency, you can get structural resonance. When these two are close together, you can get very bad structural damage. And the reason why these frequencies of these shells are very high is because we have here the formula of frequency. Frequency is a function of stiffness divided by mass. So the mass is very small, very little material, but the stiffness is very high for shells because they are curved. And so this is also geometric stiffness, right? We're getting the stiffness because of the curvature, not because of the mass. Similar like with the nets, we're getting the stiffness because of the tension. And so this is very interesting. So we developed a technique to find good shapes. I showed you a form finding technique for finding a shape for a grid shell under self-weight. This is taking into account earthquakes. So we first did this using graphic statics. So basically we just put a horizontal load, and this causes a truss line. And as long as your truss line is within your structure, this structure is going to be stable. But of course, the earthquake can come from both directions. So we mirror imaged it, offset it, and developed an envelope. We check. So basically, we end up now with this structure here. I'm looking at the bottom left figure. That's the envelope for a very good arch that will take self-weight and lateral loading, and we checked it with virtual work, and indeed we get the kind of 4-hinge mechanism that we see in arches. But that's of course in arches. What about shells? So we can actually use the same technique. We take the truss line that we find in graphic statics, but instead of taking the envelope, we now set it off with a period. We loft a surface through it, and we actually studied whether this kind of shell is very good at taking earthquake load. You might say, I've never seen a shell like that. Well, actually, this is Eladio Dieste, 1978. He built in Uruguay. He built these corrugated shells. These shells were built not because they're iconic, but because they were a very cost-effective solution to a warehouse or a hangar. And on the right-hand side, you see our proposed shells. They're both corrugated, but they're not totally the same, because with Eladio Dieste, the corrugation goes all the way across the surface, whereas with us, you might see at the top, they kind of shift, right? So it's not totally the same geometry, but it's a good base study. And so we carried out nonlinear pushover analysis. So that's basically where, for different geometries, we start pushing the shell and start seeing when the cracks start developing. So it's not when the first crack occurs, this shell fails. It actually fails if you have 4 crack zones and you get the 4-hinge mechanism, this thing will collapse. Of course, as I mentioned, we can choose the period. We can choose the period as well as the depth of the foundation. And, we see here 5 different parametric variations of the same geometry. And we also carried out the Dieste shells. And so what we see, if we apply this kind of lateral load, and we just keep increasing it until we get 4 crack zones, we see that indeed in all of the models, we get 4 crack zones, but where they occur are different. So for example, in model FF1 and in model FF5, they occur near the supports, but in the other models, we get a crack zone at the crown, at C, right? And so actually we can see that for FF2, FF3, and FF4, these are actually all geometries that have a very small corrugation depth, right? So this depth is very small, whereas for the other ones it's much wider. And that happens, so why do the shells cracks in these regions? That are the regions where we kind of have single curvature. If we have single curvature, those areas are not so stiff, right? And that means that, you know, under this increased loading, that's where they will start bending more, and where they will start, in this case we use concrete, where they will start cracking first. Here we did, in this pushover analysis, we were looking at what capacity of horizontal loading are these structures failing. And so on the left column, we have the DST one, so that is going to fail under 0.3 G. So this is actually the load of an earthquake. But, you know, any of the other geometries, so they all have the same plan area, they all have the same volume of material. The only thing that varies is geometry. And we see the one that outperforms all the other ones is FF3, right? So that has like, it will start, the 4-hinge mechanism will have occurred when we have a G of, or a PGA of 0.5. The first crack occurs at about 0.39. So this one here by far outperforms all the other shell geometries with the same plan area, same amount of material. The only thing that is varied are the corrugation, so the corrugation depth and the corrugation period. But so here is a rendering of what such a shell might look like in the San Francisco area. But actually, we all know shells don't get built that much anymore. One of the main arguments is that they're very expensive to build, because in order to build this, traditionally, we build first formwork. So basically we build a timber grid shell, a timber shell underneath it, and then we cast it on top, the concrete. Then once it's kind of cured, we remove the timber shell. So basically we're building two shells, one timber one, one concrete one, and the timber one ends up in the construction phase. So we were looking at, are there other ways that we can build these shells? And I'm going back to this shell here, which I showed in the beginning when I said, well, that one already withstood like 6 or 7 centuries of loading. The story about this one, so this is a Santa Maria del Fiore in Florence, built by Filippo Brunelleschi, who was not an architect, who was not an engineer, he was a clock maker. And the rumor is, actually, my husband sent a picture yesterday, National Geographic this week has this one on there. So there are books written about this dome, you know, about Brunelleschi, who was a clockmaker and he built this, but also there are rumors, or it's written in manuscript, that this might have been built without scaffolding, right? So we know that, but there are no documents as in how this was done, right? Even in the National Geographic of this week, it's not written how, and they should have read our paper. So I'm going to write a letter to the editor saying this is how. But anyway, so we were interested in how can you build this without scaffolding. And what we do have, and I have to say, this is a collaboration with the University of Bergamo. So we do have sketches like this. These are from the Sangallo family. They were actually the masons that worked in Italy. So we're talking Renaissance dome. They were making these domes. So they have drawings like this. This is a plan view. This is a section. What we see is, of course, remarkable, these spiraling stairs, spiraling bricks going up. We also see it's double layer dome. So we can imagine if you manage to construct the inner dome without scaffolding, you can use that as scaffolding for the outer domes. We're just interested in the inner dome. The question is, how does this inner dome get constructed? So there are some domes like this, some domes with the crossing spirals, which, you know, are beautiful. A lot of people, I think, assume that the spirals have aesthetic value, but actually they're frescoed over, so, you know, no real aesthetic value in that. So they might have served another purpose. And so we made some assumptions. So we studied this dome, which is not exactly the Santa Maria del Fiore, but it's very similar, right? This dome here, it's first of all like a hemispherical, so it means, like, you know, it's leaning inward. We also made the assumption that this was constructed layer per layer. So, you know, they would construct the first layer and then the second layer and so on. And so, so it relies on the radial geometry and on the completion of horizontal courses. And what we found really is the key thing are these vertical sticking out bricks, the ones that are colored here in dark gray. They're stuck in the layer below. And so I'm interested here in, first of all, the closed brick, but then this plate bound action. So basically what happens is, you're building your dome, first kind of like a wall, vertical wall, but then at some point, it starts curving inwards, actually a lot. And, when you put your bricks, normally they would just kind of slide inwards. But actually what happens here with this plate bound is as these bricks want to start sliding inwards, they actually collide with these vertical bricks that are standing up, right? They're slightly oriented like this. They're also stuck in the layer below. So these vertical bricks are not going anywhere, but these bricks want to slide in. They actually then start colliding with these ones and basically they get stuck. This happens from the moment that you have some friction between the different elements. If you have no friction, they still slide inwards, but of course, there's mortar there and stuff, so you have friction. And so here you see on the right-hand side, two stills from a discrete element modeling analysis. On the top, you see, imagine if there's no friction, so if the bricks would be coated with Teflon, which they weren't, they would just slide in. But from the moment you have like a friction angle between the elements of 10 degrees, they kind of stick in there and stay in there. And for masonry, the friction angle is like between 15 and 20. So that's all very interesting, right? But then the question is, how can we use these techniques today? And so I got the opportunity to work with the Create Lab at Princeton and SOM to design and build and there you see the prototyping, a vault made out of glass bricks, put together by two collaborating robots without any scaffolding. And so we were responsible for checking the sequencing and the stability all the time of the brick. So basically the robots either pick up a brick and position it or temporarily support. And I hope this is going to work. Yes, I'm going to show you, I'm going to put on the sound again, a small video, a promotional video that was made by SOM about this project. Let's see whether that's going to work. Sorry. Yeah, so actually that brings me to the end of my talk. So I hope that I've been able to show that in my research, I try to harness exceptional mechanics that you can find in these slender surfaces. And the applications are all for future-oriented, resilient and urban, sustainable urban environment. So in my lab, we study the interaction between slender structural surface and the environment, and also now under construction. We get our inspiration from, of course, it all has to be performance driven, but we get it from biology and history. And I also have a project, actually, I didn't show that, but that's what this image is from, looking at bobbin lacing. So in craft also, we have a lot of interesting mechanical systems that we can study and think like what could be the applications of those things in engineering. And then, of course, in order to study all this, we develop numerical. Also, we've started learning using machine learning, graphical and analytical methodologies to generate knowledge in this domain. I'd be happy to answer any questions that you might have.